All right. So speaking of fun things, this is Math313, number theory, lecture 21, I think. And so I promised I would start with some non-simple continued fraction expansions. Let's see if I get the camera to track me. No. And so most of the time we like to just use all ones going down here. But if you allow yourself to use things other than ones, you have some amazing things that can be done. So a lot of these expressions go all the way back to Euler. There's different notions of how rigorous are these things proved, but you can make these arguments rigorous. What I particularly like over here is when you're looking at this expansion for E, what do you think comes next?
4 over 5 plus 5 over...
So what do you think the next number? 4 plus what?
5.
So why do you think 5? So is it 5 for the Fibonacci's, or is it just 1, 2, 3, 4, and this is just something that's just haven't settled down into the pattern? And so this is one of the real challenges when you have only a small snippet. How do you figure out what really is going on? Well, in this case, it's pretty easy. Find one more term, and then that should tell you if it's going to be the Fibonacci's or not. Now, one thing is, if it is the Fibonacci's, those numerators are going to go a lot faster than the denominators. Maybe that's not a problem, but it's something to just be at least aware of. Okay, so we talked a little bit about continued fractions last time. We did the continued fraction, I think, of the golden mean, which was all ones, but we did not do the continued fraction of the square root of 2, correct? Okay, so, all right, so the square root of 2 and its very close cousin, 1 plus the square root of 2. If I can find the continued fraction of one of them, I can find the continued fraction of the other. The only change is in the constant term. Now, in general, we actually do not have good formulas for adding continued fractions or multiplying continued fractions. So while these are nice ways to represent numbers, they are not nice ways to then do operations on numbers, unless you're just doing an integer shift. Integer shifts, no problem. Has anybody ever heard of 1 plus square root of 2? It actually has a name, yes.
I don't know the name.
Okay.
I heard of it.
You've heard of it. Anybody have any guess as to what number it might be related to?
Related to the golden mean.
It's related to the golden mean. It's not quite as good as the golden mean, so what would you name it? The silver mean. Yes, it's the silver mean or the silver ratio. Right. It's not quite as good, but it's still pretty good. Okay. Yes. My kids have realized that when I say certain things, they don't know if I'm actually bullshitting. I'm sorry, trying to test their ability to discern fact from fiction, or if I'm actually telling them the truth. So I have to throw in a couple things that are truthful every now and then to keep them on their toes. And this is called the silver mean. Now, what would this make you guess that this should also be?
Bronze.
Yeah, I've never looked, but it's probably not a bad idea to Google and see, is there such thing as a bronze mean, and what would the bronze mean be? All right, so let's calculate the continued fraction of square root of 2. So the square root of 2 is 1 plus 414 ... So I'm going to write that as the square root of 2 minus 1. And this is a nice way to say, I'm just pulling out the integer part, and then what's left over is going to be a fraction between 0 and 1. What's the next step? What should I do to this fraction over here? Yes, so how? What do I do next? I normally do some... Take 1 over. This is the same as 1 over square root of 2 minus 1. And now, since the square root of 2 minus 1 is less than 1, this number here is greater than 1. And so I can now write this as an integer plus something. And I can continue this way of getting a continued fraction expansion. Now the question is, what is the greatest integer less than or equal to 1 over square root of 2 minus 1? And now we do the idea that was just suggested, is multiplied by the conjugate. How many of you remember this? They called it, I believe, rationalizing denominators back in high school or junior high school. Did they ever explain to you why you would care? It was, oh, they did?
Didn't it used to be calculators couldn't calculate things, divide by square roots? That's what one of my
Oh.
things said.
But you would first numerically approximate the square root on the calculator. Yeah. I mean, I can believe a teacher saying that, and I can also believe it being wrong.
Yeah, that's fair.
One of my friends in grad school was given a construction using just a straight and compass to construct a regular n-gon for any n. And it worked really good to construct an equilateral triangle, a square, a pentagon, a hexagon. But when you tried to do the septagon, it just missed by a little bit. And the teacher told him that's because you're not holding things down steady enough on the paper. And so it wasn't until he was having dinner one day with us at the graduate college in Princeton that we finally told him, no, your high school teacher does not know mathematics. There is no way to construct the regular septagon with straight edge and compass. There's ways to come extremely close, and it was an extremely close construction, but it was not quite right. So how would I do this? I rationalize. I multiplied by root 2 plus 1 over root 2 plus 1. And so this is now 1 plus 1 over root 2 plus 1 over, or what do I get when I multiply root 2 minus 1 by root 2 plus 1? I get 2, the inside, outside terms cancel, and then I get a minus 1, so I get a 1. Oh, that's really nice. And now you can see why 1 plus root 2 is better to look at than just the square root of 2. What's the greatest integer less than or equal to root 2 plus 1? 2. So this is the same as 1 plus 1 over 2 plus, now I need the fractional part of this, so that's root 2 plus 1 minus 2, which is root 2 minus 1. Oh, that's exactly what we had over here. So we just keep now playing the same game again and again and again, and we get root 2 is 1 plus 1 over 2 plus 1 over 2 plus 1 over 2 plus dot 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 dot. Or better, 1 plus root 2 is just all 2's. And we can represent it like that.
Can't we now extrapolate and find the bronze mean?
So, I mean, what would you guess the bronze mean would be?
3.
So maybe all 3's? So if we had all 3's, why not? If there is no such thing as the bronze mean or the bronze ratio, we will make it up right now. So we want x to be all 3's. Okay? So that means x equals 3 plus 1 over what?
3x plus 1.
But what is all this stuff in the denominator? It's x. So x equals 3 plus 1 over x squared minus 3x minus 1 equals 0. So the roots should be 3 plus or minus the square root of b squared minus 4ac would be plus 4 over 2. We clearly don't want the minus sign. So we should get, this is 13, 3 plus the square root of 13 over 2. Does anybody want to try to quickly Google this? Or should I? Alex, can you Google this? Bronze mean?
Yep.
So we will see if the bronze mean exists.
So,
Just Google bronze mean or bronze ratio.
bronze
Bronze
mean.
mean. I know the other one is called both silver mean and silver ratio.
I don't say anything.
Ah, so we might have just discovered a new number. Anybody know what comes after bronze? I know there's metals all the way down to 10th place. I don't remember the order.
It's usually green color, right?
Is copper next? I think tin is one of them. Platinum, I think, now is better than gold. I can't tell anymore on the airlines, which is the good metal to have, because gold is no longer the best. Ruby is often very good.
Yeah, bronze mean. I don't know.
Okay, yeah. No, but I mean, it seems natural to have something like that. The golden mean is all 1's. The silver mean is all 2's. Okay? So why were we able to do this calculation so easily? Why were we able to compute this without too much trouble?
Computers.
I didn't use a computer.
Recursive.
It recurses. It basically very quickly reduces to what we've seen before, right? We only have finitely many states that we can go through. And in fact, we only have one state we can go through. So as soon as we do one calculation, we see at the next step, it's the same thing. If we were to try to do this to pi, how would we do this for pi? Well, let's start trying to calculate this. So how would we start pi? 3 plus pi minus 3. So this is going to be 3 plus 1 over pi minus 3. So what would we do next?
Figure out
So does somebody have a computer they want to do this, or maybe I'll just pull up mine. So one of the things I hate is that, see, is my battery big enough? 1 over pi to pi, or pi squared, is almost 10. I know that, causes some issues with various things. All right, so I'm loading up Mathematica right now, so let's do 1.0 divided by pi minus 3. Okay, so when we do the calculation, we get 7.0625. Here it is. So this is 3 plus 1 over 7 plus now the question is, how do we want to write it?
0.625.
And just do dot, 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 dot. 0.0625 1 dot, dot, dot. But what this number really is it's really 1 over pi minus 3 minus 7, right? Well, let's think. What is 1 over pi minus 3 minus 7? Well, what should we do?
put it over one denominator.
Put it over one denominator, common denominators, right? So if we do that, we should multiply this by pi minus 3 over pi minus 3. And so we get 1 minus 7 pi. 7 times 3 is 21. So this should become, I think, 22 minus 7 pi over pi minus 3. Right? And I can check. 22 minus 7 pi divided by pi minus 3 is exactly what we had before. It's the same decimal. So when you think about this, at first this looks like it's going to be extremely bad. But we just have to figure out what the largest integer is. We move that, and then we can write this as a ratio of linear combinations of pi and constants. So this over here, we can actually write this as 22 minus 7 pi over pi minus 3. Okay, what do we do now? Yeah, 1 over. We really don't have that much we can do. We just keep playing this 1 over game. So now this is 3 plus 1 over 7 plus 1 over pi minus 3 over 22 minus 7 pi. Now this is getting a little bit more involved. So first is we can just numerically approximate this. So we want 1 over this. So 1 divided by and then we get the numerical value. It's about, it's 15.9966. Just misses being 16. So it's almost 16, but just misses. So what we would want to do is we would want to take this and subtract off 15. Okay? So in order to calculate this, I need to know pi well enough to figure what's the largest integer. Typically, that's not going to be a horrible amount of information about pi. So one of the themes of this course is I don't want to just teach you mathematics that is correct but not practical, not useful, not implementable. Right? It's fine if we have a great formula for continued fractions, but it's not fine if that formula takes so long to generate the terms that we can't do anything with it. I'm not going to prove the theorem in the book that continued fractions provide the best approximations. If you're interested, this is something you can read about. I gave you, I think, a motivation as to why that's the case. And what I want you to see right now is that it's not that bad to use continued fractions in practice. So now we want pi minus 3 over 22 minus 7 pi, and then we want to subtract off 15. So we'll have 22 minus 7 pi over 22 minus 7 pi. So we get pi minus 3, 15 times 22. I don't want to risk making a mistake. So it's 330. And then we have a minus 330 and minus the 3, so minus 333. Right? 7 times 15 is 105. And then plus 1 is 106. So 106 pi minus 333 over 22 minus 7 pi. I'll just double check. 106 pi minus 333 divided by 22 minus 7 pi. Yep, that gives me 0.996594. So that's my fraction. So what that means now is over here, I can take this, and I can replace this now with 15 plus 106 pi minus 333 over 22 minus 7 pi. And we can begin to see pi. How do you get from 3 to 7?
Double and add 1.
I'm sorry?
You double it and add 1.
Okay, how do we get from 7 to 15? What do you think comes next? Not even close. And again, this is the point of doing this. It's very easy to see patterns and get excited.
I'm always the one getting tricked.
You need to have a healthy degree of skepticism. Right? This is being done deliberately, okay? I'm working on these examples and I'm stopping at specific points on purpose. Okay? So now, but you should have known that the next thing can't be double 15 plus 1. The reason is, what's this number? This number is just a little bit less than 1. So when I take its reciprocal, it'll be just a little bit greater than 1. It's 0.9966. Come on, it's almost 1. So really, this is really plus 1 over 1, essentially. So the next number in the continued fraction expansion of pi should basically just be another 1. And then we keep playing the game. Now here's my question to you. Will I always have a ratio of linear factors like this? Will I ever have to worry about a pi squared or a pi cubed? You just got burned, or some of you just got burned in the pattern over here. I'm sorry? I should be okay?
I will say yes.
You'll say yes. Anybody else want to dance with the fire?
I'll agree with him.
You'll agree with him. Anyone else?
No, I don't agree with them.
You don't agree with them.
So you're probably right.
One of your two statements is correct. So let's assume we have alpha pi plus beta over a pi plus b at one stage. That was our remainder. What do? We write this as 1 over this, which will now become a pi plus b over alpha pi plus beta. And now we subtract off the greatest integer less than or equal to this. That's some number, right? So to get the next term, we want to write this as a pi plus b over alpha pi plus beta is equal to some integer plus a remainder. Well, if it's equal to an integer plus a remainder, I then subtract off the integer, and that will equal the remainder. Well, to subtract off the integer, I now multiply by alpha pi plus beta over alpha pi plus beta, and I get a pi plus b minus alpha pi n minus beta n over alpha pi plus beta. And so this is going to be a minus alpha n pi plus b minus beta n over alpha pi plus beta. So if I started with a ratio like this, I'm not going to have a higher power of pi come in. Is it possible that r could be a rational number? Maybe there's incredible cancellation going on here, and maybe alpha was 0, and maybe everything somehow cancels. Yes.
Because if r was a rational number, then the continued fraction would eventually terminate, and then pi would have to be rational.
Good. So if r is rational, then we're finding the continued fraction expansion of a rational number. Well, the continued fraction expansion of any rational is a finite continued fraction. Just use the Euclidean algorithm. So if you ever got a rational number here, you know that pi would then have to be rational. Pi is irrational. Okay, so this is very similar to some of the other times we've used an idea like this to refine things in this class, where if something had a certain property, that would contradict something we already know. So as we keep going on and on and on and on, we will never get a rational number. The process will never terminate. There'll be infinitely many digits, and we'll never have to do anything worse than a ratio of linear combinations of pi and constants over pi and constants. Just first degree in pi over first degree in pi. That's kind of nice. What it means is we can compute the continued fraction expansion of pi without too much trouble. Now, in the 21st century, by we, I don't mean us personally. I'm surprised I actually had the patience to go down as far as I did here. What do I mean by we? So what is we in the 21st century? The computer. And so pi is equal to 3, 7, 15, 1. I think it's 292 next. 1, 1, 1, 2, dot, dot, dot. I'm sorry?
He said what?
Oh, okay. You want more digits? Mathematica just calculated 1,000 digits. Okay. It goes 1, 3, 1, 14, 2, 1, 1, 2, 2, 2, 2, 1, 84, 2, 1, 1, 15, 3, 13, 1, 4, 2, 6, 6, 99, and so on and so on and so on. So the continued fraction command isn't that bad. As a really nice exercise, I strongly encourage you to write a computer program to calculate the continued fraction of pi. What else might you want to calculate the continued fraction of? E.
Is there like an exponential distribution of those numbers?
In terms of how often we have each number?
Yeah.
So this is one of the big questions. So there's a beautiful result called the Gauss-Kuzmin theorem. And in the book I wrote on number theory, I heavily take a beautiful exposition by Kinchin and provide a lot of the details. And go through, there is a formula. I think it's around 40% of having the digit 1. And I'm trying to remember, it's been a long time. I want to say it's like the log base 2 of 1 plus 1 over k plus 2 is the probability of a digit of k. It has been a while. Gauss, Kuzmin. I don't know what they did before the web. Oh, I was so close. Or maybe it's the same, but where things change. Okay. They say that the answer is a negative here and a negative k plus 1 squared. Okay. All right. So this is the probability of observing a digit of k for a generic continued fraction. So this goes back to what is a generic continued fraction. Almost all continued fractions will have a probability of a digit being k equal to this in the limit. Give me an example of a generic one. That's extremely hard. Now, of course, we could construct one, and we can just jerry-rig the frequencies to be right, very similar to the Champerron's constant. But numbers like pi and e, do we expect pi and e to satisfy this? This has a lot of ones, but maybe not enough, because I think it's around 40%. So if we do the negative log and then it was supposed to be, we put in a 1, so that would be 1 minus a 4, so it would be 3/4. So it's about, okay, I was right, it's about 41.5. So am I going 41, 42%? My memory's not too bad, I just had the formula a little bit off. So k equals 1, it's about 41.5%. But in terms of what is a generic continued fraction expansion, very open problems. When you start looking at pi, you start to see a lot of ones, and you might be a little suspicious, but then actually, if it's supposed to be about 40% ones, maybe that's not so bad. So our goal is to try to find good rational approximations to pi. All right, so one possibility is, of course, does somebody have a computer open where they can just give me a bunch of digits of pi? Or people can just multiply it out. 3.14159.265. Is it 3.5? Okay. 3.5.8.9. Okay. 5.7.
Like 8979.
8979. Okay. All right, so that should be enough to start with. All right, so that's a start for pi.
3.23846.
Okay, so let's look at the continued fraction approximations for pi. Our first approximation is 3. Right? I'm really not expecting to do much better if I'm just using an integer. The next one is one of the more famous ones, 3 plus 1/7, also known as 22 sevenths, which you might have heard of. And what's 22 sevenths? 3.1428, I think. 2857. And then that would be repeating. So just using a denominator as large as 7, we've got 2 decimal digits correct, and then we've got a 28 instead of a 15 for the next two. It's not horrible. Let's look at the next one. So it's now going to be 3 plus 1/7 plus 1/15. So there's a mathematical command that goes backwards, and so I'm just trying to just put that in just to save some time. It's from continued fraction. Okay, I thought that's what it was. So if I do from continued fraction of 3, 7.
That's cool.
Making you scope it. Like doing 3 plus 1, 7, 7.
Yeah, no, I was just trying to.
I think it's on the board already, right?
Yeah, you know, but I'm from. No, there's just a. No, all right. All right. So what's this next one?
3.15094.
3 point.
1415094.
And what's the fraction?
Oh, I'm using.
It should be 330 or yeah.
All right. So it's 3 plus 1 divided by 7 plus 1 divided by 15. I'm just forgetting the Mathematica computer right now. 333 over 106.
Yeah.
So now if we just go up to 333 over 106, we're getting 4 digits right. Instead of 26, now we have basically 9 or 10. It's not bad. The next one would be 3 plus 1 over 7 plus 1 over 15 plus 1 over 1. Do we expect that to be a good or a bad approximation?
Pretty good.
Pretty good. Why pretty good?
Because the next one is 292.
Yeah, the next one is a 292, so we should replace this 1 with a 1 plus 1 over 292. Well, 1 plus 1 over 292 is essentially 1. So it's not going to change by that much. So whenever you have a really large number, hopefully the one right before should be pretty good. So this is almost the same as this. All I have to do is change the 15 to a 16, right? And if I do that, I get 355 over 113. How many of you have seen this continued fraction, I'm sorry, this rational approximation for pi? This is one of the old ones that people have known about for a long time. And so if we take that, 355 divided by 113, and then one of the problems sometimes is telling Mathematica to just give me enough digits. Okay. So this is 3.1415 929 That's pretty good. So we've got 1, 2, 3, 4, 5, 6, and then instead of a 6 we have a 9. So we've got 6 decimal digits correct. And we're using a denominator that only has 3 digits. And just barely. I mean, 113 is almost 2 digits. That's not bad. This is the power of continued fractions. If we were to try to get this many digits before, we would have, 3141592, 6 over 1000000. So it would be 1, 2, 3, 4, 5, 6. So maybe like around 10 million would be the denominator. And so we're trying to just do a naive brute force search to find what's the best rational approximation with the denominator up to 10 million. That's a lot of work. The continued fraction gets it very quickly. Now we stopped at 15, but we knew that this number was so close to 1 that the next thing over here was going to give us 1 for the next digit of the continued fraction. So we were able to do this with very little work on the board and get a phenomenally good approximation. Yes?
Haven't we only been able to do this though because we already know what pi is?
Well, we know approximately what pi is. And so then the question becomes, how many decimal digits of pi do we need? So for instance, for doing these calculations, do I need to know pi to this many decimals? So we need to be able to do things well enough to figure out what the greatest integer less than or equal to each of these numbers are. Now, one way of knowing this is, well, if I know pi to a huge number of digits, if I eventually get to the point where I have the first 20 digits. Whenever I'm doing these things, and I'm multiplying by at most 100, maybe it's only going to change things in like the 17th digit or later. And that's enough so that I can say, as long as I'm not too close to an integer, this is not going to be enough to push over. Now, because we had 15.9959 or something like that, something that was really close to 16, we do need to know pi to a couple of digits to be safe. But then the question becomes, what's the good approximation? So we can actually take a reasonable approximation to pi that's good enough to calculate these things and then use that to get a much better rational approximation. Okay? Any questions about this calculation? It turns out that there's a class of numbers where you can calculate the continued fraction expansion very easily. Much easier than this. So the issue you have, and I'll put some links on this, is a real issue in terms of how well do we need to know pi to run this. And it becomes an interesting question, how many decimal digits do I need to get, say, the first k continued fraction digits correct? And then from the first k continued fraction digits right, I have a really good approximation to pi. Could I feed that in and do some kind of looping like this? That now, if I actually had a result that told me how good of an approximation this is. Oh, we do have results like that. We have Dirichlet's theorem about you must approximate to at least 1 over q squared. We can actually make some good statements. This must be actually maybe 1 over 113 squared. And then that might be enough to then calculate more digits. And so what's nice is our confidence, our value, our knowledge of pi is growing, and then we feed this in and get even more information about pi, and then we feed that in and get even more information about pi. And then what's nice is, for these calculations, if I have a rational that's just a little bit lower and a rational that's just a little bit higher, I now have a little band. And I can see how that band grows and changes over time. And as long as I make sure that I stay accurate enough so that this band is not split with an integer, I'll know exactly what I should do at the next stage. The difficulty was if we had 15.996. If my range was from somewhere between 15.994 to 15.998, great. I know my next digit has to be 15. But if my range was now 15.994 to 16.0003, crap. 15 and 16 now both fall in that range. And I don't know now what I need to do next. I now need to refine my estimate. I need to get more digits. It turns out algebraic numbers. There's a beautiful formula that allows you to calculate the continued fraction expansion of algebraic numbers by using the minimal polynomial. And it turns out what happens is it uses some of the fundamental techniques we've been talking about all semester. You cycle through so many possible cases. And there's certain space you're looking at with certain possible coefficients. It's all very computable, and you can do this and keep track of everything. So again, this is a vast subject. This is meant to just give you a sense of what's out there. Continued fractions have sadly decreased in popularity, but it's phenomenal what can be done. It turns out that you can do continued fractions for more than just a number. This is a little bit strange, but what else might you want to do a continued fraction expansion for? A polynomial, or a function in general. So if I give you a strange function, you could ask, what is the continued fraction expansion for this function? And then frequently what happens is the number you care about is a special case. And then, I wasn't planning on doing this, but given that I've been having so much fun with you today, I'm going to write the continued fraction expansion of a number. I'll just write the first couple of digits. And so I'm going to ask two questions. Can you guess the number? And can you guess the pattern, if there is a pattern, or say that there's no pattern? Just want to make sure I do this right. Any thoughts on the number? E. Seems pretty reasonable, right? If I just take the first few, 2 plus 1 over 1 plus 1 over 2, I think I dropped a parenthesis. Sorry. 1 plus 1 over 1 plus 1 over 2 is 8/3, which is 2.66. So if I don't go too deep, I already have 2.66. What's E? 2.71. This is looking pretty good. So this was just going the 2, 1, 2. If I do 2, 1, 2, 1, that just changes the last 2 to a 3, and I get 2.75. Well, that's already interesting, so that the continued fraction is actually hopping between being above and below. And so you might be converging to the number from below through the odds and above from the evens, or vice versa. But given that E is around 2.71 and I've got 2.67, 2.75, it seems quite likely that this is E. Thoughts on the next number? And the next? And the next? But if that's the case, why was I looking at my computer to see what the next numbers were? So do you really think it's now 1110? So how many think it's 1110?
I'll go for it.
No, go for it. How many think it's not? If it's 1110, why was I looking at my computer to carefully write the digits?
Maybe it changes after 1110.
They would keep us on our toes.
Just keep you on your toes. It's 1110, 1112, 1114, 1116. Two of my friends dropped out of college for a year to help the amazing James Randi set up his Magic Institute to debunk people's claims of psychic powers. And so I didn't get to hear all the secrets that my friends did, but I got to hear some of the things, and I'm not going to say this with the camera rolling, that the amazing James Randi would do to misdirect people. And some of the things he would actually say in public. So one of the things I can mention is, he was speaking at a podium, and then as he walked away from the podium, it got harder to hear him. Why did it get harder to hear him as he walked away from the podium? Yeah, the microphone on the podium, and as you get further away from the microphone, it's harder to hear. The microphone was off. There was a microphone built into his shirt that he was controlling with a device in his pocket. And so he would just turn down the device as he walked away from the podium. It's all to get you to look at the wrong things. And so, part of the purpose of today's lecture is just be on your toes when you see things. It's not a bad idea to look for patterns. It's not a bad idea to try to prove patterns. But just because something is holding for a while does not mean it continues. Okay, so this is basically all I want to do from chapter 6. There's more on continued fractions. If you want to look at that, that's great. But this is really what I want to do for chapter 6. All right, I want to do one more thing from chapter 7. And this is going to lead into a colloquium that we will get in another week or two. It's talking about when can you write numbers as sums of squares, sums of cubes, etc., etc., etc. Right? So this is a classic problem. We've already done some of this. So this is the last part of chapter 7. Chapter 7 goes into a lot more detail. Since we're going to have a colloquium on this, I'm not going to spend too much time on this. So the question is, which n are the sum of two squares? And more generally, which n are S perfect kth powers? Or are the sum of S perfect kth powers. So I want to say, when can I write n as x1 to the k plus xs to the k? And this is called Waring's problem. We actually solved it when k equals 1. When k equals 1, it's the cookie problem. And so this had a combinatorial solution. And it had a generating function solution. And it turns out it's the generating function solution that generalizes to the other case. And later in the semester, we'll probably have a lecture on the Hardy-Littlewood circle method and how you attack problems like this. Some of the most active and, in my mind, beautiful mathematics and number theory. It's how you make these problems accessible. So let's try to prove some weak results. Do you think every number is a perfect square? No. So give me a number that's not a perfect square. 3. And in fact, there's infinitely many numbers that are not perfect squares. Very few numbers are perfect squares. So the next thing you could ask is, well, maybe every number is a sum of 2 squares. So is every number the sum of 2 squares? What do you think? And I want it to be non-negative.
3.
All right, so 3 is a problem. So we'll just declare 3 is no longer a number.
7.
All right, we will say that 7 is too closely related to 3 and is not a number.
6.
6 is also closely related to 3 and 7 and is not a number.
1001.
Also, I will throw 1001 away. So here's my question. What if I could only throw away finitely many numbers? Maybe there's a couple of numbers in the beginning that are problem children. And once I get past them, everything is fine. So can you prove that there are infinitely many numbers? And so there's a lot of ways to do this. You'll see some ways, I believe, in the colloquium. But I'm going to show you a quick counting way. If I want to write my number as a sum of 2 squares, let's say I'm looking at all n less than or equal to x. And so I want to write n as a squared plus b squared. What can you tell me about a and b?
They can be written as squares.
I'm sorry?
They can be written as squares as well. As a sum of
Well, okay, one thing is I could write them as squares, but how large can a and b be?
most.
At most, x.
Oh, X.
A and b are less than or equal to x. So if I'm trying to write all numbers up to x, well, in fact, they can't be as large as x. How large can they be? Square root of x. So without loss of generality, we can assume either a is strictly less than b or a equals b. How many numbers satisfy this condition with a equal b? Just square root of x. How many numbers satisfy a less than b where a and b are less than or equal to square root of x?
Roughly X.
Why roughly x? Not quite.
Wait, X over 2.
It's basically root x choose 2.
Yeah.
Maybe I got to be a little careful because I have 0, but look, I want to choose 2 numbers that are distinct that are at most x. So I have root x choose 2 ways of doing that. And then I have x numbers where a equals b. Well, root x choose 2 is root x minus 1 over 2 factorial. That's about x over 2. So this whole thing is approximately x over 2. So what this tells you is just by simple counting, you know you can get at most half the numbers. So we can't write numbers, we can't write all numbers as a sum of 2 squares, and in fact, infinitely many are going to have to fail. What about sums of 3 squares? Could that be possible? Yeah, because if now I'm doing, root x choose 3, I'll get root x minus 1, root x minus 2 over 3 factorial. That's x to the 3 halves over 6. That's possible. So we'll see much more about this in a colloquium, and I will encourage you all to attend that colloquium. All right, this is a good place to stop. Enjoy the weather. We are finally getting nice days again.